Hi, welcome to Upward Bound Physics, Day 2 on acceleration. We'll be using ramps, kinematics, and graphing. Acceleration. Velocity is not always constant. When velocity changes over time, this is acceleration. The average acceleration is if an acceleration is constant. That means the velocity changes at a regular rate over a period of time. That acceleration that is calculated is the actual average acceleration because nothing is ever actually perfect. You have your three basic kinematics, 1, 2, and 3. And the graph, so here's what you need to know about acceleration. The graph of an xt, or position time graph, will now be a curve. The vt, or velocity time graph, will now be a sloped angled line. And the at, or acceleration time graph, will now be a flat line showing that constant acceleration. Graph translations. The slope of an xt graph is equal to the velocity. The slope of a VT graph is equal to the acceleration, and the area under a VT graph is the displacement. The area under an AT graph is the change in velocity. So when starting a problem, you're going to first always do a TÜV chart. You're looking for distance, time, velocity, and acceleration, but not every term will be found in every problem. Remember, you do or you should have a master TÜV chart of distance, time, velocity, and acceleration, all the units and variables and equations that go with them. So example 1, a ball is pushed with an initial velocity of 4 meters per second. The ball rolls down a hill with a constant acceleration of 1.6 meters per second. The ball reaches the bottom of the hill 8 seconds later. What is the ball's velocity at the bottom of the hill? So in the TÜV chart, you're given meters per second, you're given meters per second, you're given the word acceleration, you're given seconds, a unit of seconds, and you're asked about the velocity at the bottom. So your V naught, your initial velocity is 4, your acceleration is given as 1.6, and the time given is 8. So solving that problem using kinematic 1, V is equal to V naught plus AT, V naught is 4, A is 1.6, and T is 8. Units do work out to have a final velocity of 16.8 meters per second. Example 2, you're given velocity time data. What is the displacement of this object? So the displacement, right, can be found by constructing the VT graph first. Remember our multi-level step approach, you do still need to be able to do all of those things. So what I would do is draw the VT graph first, and then I segment my graph. I separate my rectangle at the bottom from my triangle and find the area of those two shapes. So the area of the triangle and the rectangle is 1/2 the base times the height plus the length times the width of the rectangle. In physics, this is 1/2 the time times the change in velocity plus the velocity times the time. Working this out with units, we get 144 meters. Now, the other way to find the displacement, or how far the object has traveled, is simply based on the kinematics. When you're given the equation of the VT graph, V is equal to 12 plus 4t, we use a default starting position at the origin using kinematic 2, x is equal to x naught plus v naught t plus 1/2 at squared. We can substitute in those values that we know for kinematic 2. Units do work out, and we get the same answer of 144 meters. We'll finish the complete multi-view profile of these problems in class. Thanks for watching.